Recognize your different states of matter. So, Maria, can you tell me one of the states of matter? Okay, so liquid is a state of matter. Clauby, what's another state of matter?
Solid.
Very good. Breslin, the last state. Very good. Which state of matter did we just talk about in our previous unit? Yeah, we spent a ton of time talking about gases, right? There's tons of time talking about our gas and gas laws specifically. Now, if I was to do a change, if I was to do if you will, a change from one to the other, you see those little double-sided arrows there, which means I can go back and forth. Would that type of change be physical or chemical?
Physical.
Very good. Physical change, and that's a physical change there too. So right away, I think one of the statements that you could be making off to the side is that a state change, so when you change states of matter, they're always physical changes. So let me ask you this question. Do you know what this substance is?
Water.
What is the chemical formula when it's in the gas phase? It's the exact same. What is the chemical formula when it's in the solid phase? Do y'all remember drawing out Lewis structures? I drew this out yesterday for water. Why don't you draw out the Lewis structure of water? And if you need help, if you're like, I don't know what this is, then you want to. This is a breakup in the classroom. There's the people that are getting it right now, and there's people that I don't know what you're talking about. If you're an I don't know what you're talking about, watch what I do. Oxygen has 6 valence electrons. H has 1. So there's going to be a connection right there and right there. So then I could redraw the Lewis structure there. And I could redraw the Lewis structure here. I think y'all follow that logic, correct? But look, is it water each time?
Yeah.
So it's always water. You're not doing a change of a new chemical substance. You have the same substance between the change. Now the difference is the compactness and just the orientation. So I'm going to get you to draw something just a tad different. Under the solid heading, I'm going to get you to draw this setup. Draw that real quick. In which case are your particles the most ordered? Solid, liquid, or gas? So, very ordered. Which means the gases are very disordered. You could use the term random there, I think, too. In which case is there a definite shape? Definite shape. There's also with solids a definite volume as well. Now, liquids have definite volume, however, they lack a shape that's definite. Their shape is dependent upon their container. It has neither or neither. No shape or volume. Because it's really hard to control gases. Anyone get the coffee? Okay, don't stunt your growth. What's the name of the formula? Or what's the formula for this substance? H2O. Right? So this is definite volume. How would I measure this out for volume? Milliliters, right? Is this a definite shape? The shape's based on the container, right?
Yeah.
Any proof? Is that the same shape now? Is its volume the same?
Kind of.
Yeah, its volume's the same. You didn't see any water go anywhere. Well, you saw it go on the ground, but it didn't just disappear. The volume is maintained, but the shape is obviously lost. Right? No, we just won't walk over it for a while. Very good.
Then you change it to a gas.
Eventually.
Eventually.
Eventually. Okay, very good. So let's move on and let's keep talking about this because I think we're making good headway. Now this is getting into yesterday's notes just a tad. How do I do that change to go from solid to liquid to a gas? What am I having to make happen?
Condensation.
No. I'm saying what do you have to add to go from a solid to liquid?
Energy.
Okay, so add heat, and heat is a form of, we said, what? Energy. Cool. Now, I'll one-up you from yesterday, and I'm going to ask you to take a second, find a shoulder buddy. Do y'all know what a shoulder buddy is? That's a local friend, okay? That's a neighbor. Not as in there's a neighbor next door in my house. You don't need to go ask them because they're way too far away. Ask a friend around or work with a friend around you. I want you to write something in this area right there that kind of mimics this situation. So I'm going to give you 20 seconds to come up with what you want to write in this little area real quick. Very far apart. Let's talk about how they would look in a container real quick. So I'm going to make this my container. And let's maybe talk about water because that's just kind of the thing you go to. So let's talk about maybe a water bottle. If I put water and I let it be a solid, that's called ice. Or if I let it be a liquid, that's just normal water. Or if I let it be vapor, so the gas phase. I want you to work with your shoulder buddy again, and I want you to draw little dots that represent where your particles would be. So if I had a container like a water bottle that had gas vapor, where would the particles be, or liquid or solid? And let's say maybe another 25 seconds with your shoulder buddy. Let's kind of review real quickly this concept of density. Let's draw out the density triangle as a reminder. Here's your density triangle. DMV. I always think when people are like, how am I supposed to remember that M is on top? I always think of mountain first off, and that helps me out. Or I think of going to the DMV. Do you know what that is? Department of Motor Vehicles. You've probably been there before. You spent probably about a good day there in line. That's the DMV. What does the M stand for in density?
Mass.
And the V stands for velocity, right?
Volume.
Very good. Good catch. And the D is for,
Density.
obviously, density. Hopefully you wouldn't miss that because it says density right above. Now, what's the unit of mass typically? Hopefully we're all still paying attention, right, Grayson?
Grams.
Perfect. What's the unit for mass?
Grams.
Grams. And what's the unit for volume?
Milliliters.
Typically, okay, milliliters or liters. Perfect. Which means the unit for density is going to be perfect. Grams per milliliter. Grams per milliliter. Cool. And just as a quick review, I'm gonna post up a question about solving for density. I'm gonna get you to copy this down, and I just want to do a review of density real quick. Two types of questions. This is meant to be extremely short and somewhat fun. So let's go for it. Let's do this. Oh no. It's there. I'm gonna get you to copy this bad boy down real quick. This is your problem. Yep. This is your problem. So let's go ahead and write this out. Here's problem number 2. You know, we've all got problems. I've got a lot of problems today, as you can see. Substance A, B, and C. We got 3 guys, I'm trying to tell jokes up here right now. We got 3 substances. Guys, can I tell my jokes? We got 3 substances. Each of them has their own density. I'm going to get you to write out these densities. 4.76 grams per milliliter for substance A, 0.872 grams per milliliter for substance B, and then let's see, 1.00 grams per milliliter for substance C. And let's say I pour them all, they're all liquids, I pour them into this massive little beaker. This right here is a beaker. You know what a beaker is. It measures liquids. Or actually it holds liquids. It's not really good for measuring. And it forms 3 layers. There's my 3 layers of liquid. This is a liquid right here. I'm going to get you to label him and label him and label him. Now, one of these liquids is A, one of them is B, and one of them is C. And I want you to put down real quickly which of these is going to be A, and which is going to be B, and which is going to be C. Maybe this is top one's A, maybe this one's B, maybe this one's C. I don't really know yet. I haven't solved it. But I want you guys to solve it real quick. We'll give you another, let's say, 35 seconds real quick. This is a jam right here. I think it would be best if I put A on bottom, then put C, and then put B up top, so it reads BCA. Raise your hand if you got this question right. Very good. Is A the most or the least dense object? Most dense. And B would be the least dense. If one of these substances was to be water, which one would be water, B, C, or A? Actually, C would. And that's because water has a density of 1 gram per milliliter. Did y'all know that? That's the density of water? Cool. Water has a density of 1. You might want to definitely jot that down real quick. Now let's take a break because I know we've been doing chemistry for like 10 minutes real quick. So I'm gonna take a break and I want to give you just a music trivia quiz. You guys know that I used to be a DJ, right? I think that's pretty much common knowledge now. And I have a lot of good songs. I have a song for you I want to play, and I want you to tell me what movie this is from. And I'm gonna play just like a small piece of it. I'm not gonna play a long, snippet of the song, just a little bit of it real quick. And I want you to tell me what movie this is from. I was thinking about this song earlier on the radio. It's really cool. Yes. Okay, this is right down in the blank. Okay, that's really enough of that song. So the name of the movie is what? Titanic. Like one of the highest grossing films of all time. Did y'all know that? Probably one of the most popular movies back in the day. But I actually went there for a reason. Let's talk about Titanic. Obviously you all know what happened to it. What happened to it? So it sank, right? Because it hit an iceberg. So you've got Titanic, which is this massive ship. There's little Titanic right there. And there's the massive iceberg, right? And of course, do you know what ocean they're in? Yeah, so they're in the Atlantic. And the Atlantic, of course, is extremely cold during that time of year. And actually, we're getting pretty close. I believe it's like April the 10th or the 11th maybe is like the day that it sank in what does anyone know what the year? 1912, I believe, actually. So we're actually almost at the 100-year anniversary, I'm pretty certain, of Titanic sinking. But I go over this for sure because it hit an iceberg, correct? Yeah. Now, typically, when we look at B, C, and A, which would you think is going to be the solid, B, C, or A? You would usually think that A is the solid, C is the liquid, and B is the gas. Typically, it works out. Think about it. Where's the water at right now? On the ground? No, I'm saying where's the water at? It's on the ground now, is it not? Yeah. Where's the gas? Is the gas above it? Obviously, it's above that water that's on the ground, correct? And what's right below the water? the solid. So that's the way it typically works out. However, when Titanic sank, it hit an iceberg, and that's a solid that's above the liquid. And the reason I go over that is because I want you to see that water itself is more dense as a liquid than when it is a solid.
Is that why the iceberg is floating?
That's why the iceberg floats, or that's why the ice in your glass would float just as well. Whether it's an iceberg or the ice, it's gonna float. And I'm saying now that that's something that you should not expect, because usually the solid phase is the most dense phase. So the question is, why does the ice in the glass float? And the logic or the reasoning behind this is because of the polarity of water. Now, we've talked about polarity a little bit before, but let's redraw out the structure of the water molecule real quick. There's your water molecule again. What are those little dots up top? These right here are electrons. What's the charge of an electron?
Negative.
So it would appear as though this side of the molecule has a very negative charge because of all those valence electrons, and this side of the molecule would have a very positive charge. You create a polar molecule. When you think of the term pole, you should think of like north and south pole, like on a magnet. An area where it's very negative, as we see up here, and an area where it's very positive, as you see down here. Now, what if this pin top, introduce the pin top, what if this little pin top was negatively charged? Would it travel to this side? No, because negative and negative do not like each other, right? It would travel to this side. What if this pin top right over here was positive? Would it go to the bottom or to the top? So it'd go over here, right?
Yeah.
Okay, so we can see that there's this idea, this polarity concept that would be applicable. So what if I introduced another water molecule? It would make sense that the oxygen end would want to go to this side, just like that. What if I wanted to put another water molecule right through this zone? I probably should put my H right there. Does that make sense why I'm doing that? Because I'm allowing for a connection piece right there, or right there. What if I drew in another water molecule? I could put the O right there. It would make sense to put the O exactly right there to allow for this interaction and this interaction. Do y'all see how this is working out? What we're getting is some points because of polarity. We're getting how water molecules are self-attractive. So water molecules attract other water molecules. This forms a special type of bond called the hydrogen bond. And because of this, it gives water some very unique properties. And we will be talking about a lot of those properties over the next couple of weeks. But one major property that we just discussed was the density property of water, and how crazy it is that water can float as a solid and not sink as though you would suspect it to. So here's what we're going to do. We're going to take another break real quick. I'm going to prompt you with a question, or kind of a question you could say. I want you to draw, so here's your task. A task is something you have to do. So here's your task. I want you to draw four water molecules, or more if you wish, of H2O. And I want you to show with dots, just like I did earlier with my red dots. I want you to show the hydrogen bond. And again, just to point you out, or to point out this from earlier, the red dot system that I drew out up above, are we still all paying attention? I hope we're all paying attention. Those dots, those red dots, those were the hydrogen bond associations. So here's your task. Draw out 4 molecules of water, and I want you to draw out the dots in red that are the hydrogen bonds. And I'll give you maybe 1 minute and 10 seconds to go ahead and do that real quick.